So in this part of the Advanced Lab introductory experiments, we're going to go and discuss one of the very common techniques in use, which is all about spectroscopy. Okay, so we're going to start with giving a basic overview of the concepts involved behind spectroscopy, the whole range of the family of different techniques, which are broadly come under the same category of being spectroscopy. We'll talk about radiation sources that one might use in the spectroscopy experiment, so particularly lasers or white light, but also mention a little bit about X-ray production. We're going to talk about detectors, so particularly photoresistors, photodiodes, transistor-based devices, and photomultipliers. I'll give a couple of examples of sort of real experimental setups where spectroscopy features. And then finally, we'll finish by looking at spectroscopy beyond light. So where the spectroscopic source we're using is not electromagnetic radiation. Okay, so let's start by supposing that we have an unknown object. We've discovered an unknown object on the surface of the moon that we want to learn about. Obvious references to Arthur C. Clarke's 2001. Okay, so what are we going to go and do? Well, spectroscopy describes a whole family of different techniques where essentially you're using radiation to analyze materials property. So as it's very kind of crudest and simplest, kind of we do spectroscopy anyway. Kind of without any scientific instruments, or hardly any scientific instruments, what you'd be looking at here would be providing some sort of stimulus to the experiment, which would be diffuse visible light from some kind of visible light source, table lamp. So that's going to be operating in a range of somewhere between 450 and 650 nanometer wavelength light. You might have a modicum of optics to go and help with that experiment. So a lens, a magnifying glass, and your detector is basically your eye, and that's really all you've got to go and work with. But it's still a spectroscopic experiment, just a rather limited one. So in the simplest form, we're shining visible light onto an object and we're analyzing it with the eye. And well, what can we get out of this? The sort of information we're able to collect, well, the color, so an RGB value, because of the way the eye works. It's only sensitive to the visible light range, and even then it decomposes into three components. Reflectivity, whether it's specular or diffuse, but not really much more than that. And what you might say the macrostructure, so its shape, and possibly maybe if it had any kind of texture or anything else on the surface, but we're talking about structure at the scale of millimeters at best. Okay, so of course that's not really a very exciting experiment to go and do, so one might want to try and make some improvements and see what else we can do. So go for a little bit more advanced and start trying to use more controlled source optics and sources, and generally get a slightly more sophisticated experiment. But we still have the same pattern. There's still a stimulus. So we might choose to say use, in this case, a xenon mercury lamp. So this is a light source which will produce a very intense output across a broad range of wavelengths. So if you have a large energy output across a broad range of frequencies or wavelengths, then that is a white source. And in this case, that'd be a white source in the range 300 to 700 nanometers. So it goes into the near UV and extends a little bit below red light. So it's got really a broad, but still basically essentially visible light. We might then also improve the optics we use before we shine that radiation onto our object. So in this case, some collimation, so that we know that the light is going through parallel to the one direction. And we think about what we might be able to go and do with that. Well, we might be able to look at a transmission signal, so seeing what's getting through. And then what we need to go and do is to separate out the different components of that transmitted light. So you might use a prism, or you might use a grating, so that you can detect individual frequencies or wavelengths separately. And in this sort of experiment, what you'd probably be looking for is to look for absorption lines in the output. Alternatively, you might also want to go and look at the reflected signal. So in that case, again, you would go and send it through some kind of grating or prism. So you might detect a direct specular reflection. That's probably, well, I was going to tell you some information, but if you look at some angle where the angle of incidence and the angle of reflection are not equal to each other, then you're going to be looking in particular for things like emission lines. So are you, with your incident radiation, are you exciting some energy transitions in the material, which are then giving you an optical emission? So putting this all together, if we're looking at the transmitted line, then you're looking at things like capacity, you're looking at things like refractive index, which is telling you about dielectric constant. You're possibly looking at the band structure, or particularly if you're looking at the cases of gases or isolated atoms, then it's telling you about an atomic composition. If you're looking at the emission information, then it's going to be telling you possibly things about molecular structure. It'll be telling you about atomic composition again. Could be telling you about things like carrier density and obviously reflectivity. So charge carrier density and reflectivity. So these are the sorts of information you're starting to get once you go beyond the just look at it and go, is it shiny? Okay, so in general terms, however, spectroscopy is the use of any sort of radiation. It doesn't have to be optical light. So it's possible to use non-optical sources, in which case what you're able to find about it, the observables you're able to measure, are going to be determined by the energy or the wavelength of the incident radiation. And there's the very few properties that you can't in fact get at by observing the effect of stimulating the thing you're interested in looking at with the correct stimulus, type of stimulus. So pretty much you can get at most properties one way or another. So for example, if you use X-rays as a stimulus, so there you're looking at sort of wavelengths which are a fraction of a nanometer. Well, in the first instance, the reflected light, the scattered X-ray light, can tell you an awful lot about the structure of the material. So it's going to tell you things about crystal structure. You can find more about nanoscale structure. You can find information about density, molecular geometry. So, for example, famous examples of where we've used X-ray radiation, X-ray scattering to figure out the structure of DNA, the double helix experiment, and of course the original X-ray scattering experiments were done by the Braggs, and of which the father got the Nobel Prize in. Father was in Leeds, got the Nobel Prize, and his son, who worked out the theory, who was based at some other university called Cambridge. If you look at the transmitted X-ray information, and you can then make a spectra of that. So X-ray absorption or transmission can give you a lot of information, particularly can give a very complete picture of the composition in terms of elements you've got there, and also start giving you information about the bonding and the chemistry of what's going on. And if you play some tricks with how you generate the X-rays, you can get information about the magnetic structure as well in the material. So you're starting to get into a very detailed picture of what's going on in this material just by switching from an optical stimulus to an X-ray stimulus. And again, you can do the same for other non-optical sources. So to reiterate then, the key things are that spectroscopy has several key components that are basically the same for all forms of spectroscopy. So you have to have some kind of radiation source or stimulus source. And so the parameters you're interested with there are going to be things like the energy, the wavelength, the frequency. You've got to have some kind of optics of some description. So focusing, collimating, monochromating, so making sure you have a single well-controlled wavelength. And then you obviously have your object you're looking at. And then on the output side, again, you've got to have some signal processing optics. So you might be doing things like dispersing or filtering. So dispersing by wavelength or frequency, filtering to capture only particular frequencies or wavelengths, or looking at some kind of reflection angle. And then the final part of the set of a spectroscopy setup is you will have some kind of detector. And there you're interested in things like the sensitivity, the energy scales on which it can work, the sampling rates at which it can work, resolution, all of these things that we've talked about before in terms of how a sensor or a detector works are going to be important in a spectroscopy experiment. So in the rest of these videos, what we're going to do is talk you through each of these stages in turn. Well, the radiation sources and the detectors. Not say so much about the optics at the moment because that depends very much on the particular type of experiment you're doing, but we'll then give some examples and discuss exactly how those components are all fitting together.